Oh, goodness. All right, let's get started. So I don't really have a whole lot in the way of major announcements. One thing I will mention to everybody in here so that you are aware. I think, is everybody in here in steel? I think everybody in here is in steel. Okay, all right. So here's what's going to happen next Wednesday. We are going to have concrete in class. We are not going to have steel in class. Okay? The reason why is because scheduling the senior design presentations was a nightmare for a number of reasons. I've got 6 different teams. They all have different class schedules to where they can meet someday or sometimes and they can't meet others. I have the faculty who are coming in to review them. They have their own class schedules. And then on top of all of that, we have a candidate on campus for a faculty position. And so some of us are meeting with the candidate one-on-one. And so that caused a scheduling kerfuffle. So it was very, very difficult. And the only way that I could schedule the presentations was to use the time in steel design. So what we're going to do on Wednesday, we're going to have concrete in class. We're going to have steel as an online lecture, and we are not going to meet on Friday like we had originally planned. So if it's weird that you're coming for concrete and not for steel, that's why. So everybody okay with that? Well, I mean, you have to be. I don't care if you're okay with it. Take that. No, I'm not that mean most days. Okay, so I have here an image. This is essentially the shear diagram that we ended class with last time, just plotted pretty in Excel. So it's not like this is any different than what we came up with last time. So did anybody have any questions with coming up with this diagram? Everybody okay with that? Now we haven't done any design yet, but this is where it starts. Okay. Now what we had arranged or what we had come up with was we came up with a few other things. So let me write out a few other things that we came up with. So here's the image. I'm going to drag this over. And then there was a few other things that we should add sort of on top of this. So first off, we know that PVC wasn't it something like 37.95 kips. I think that was one of our values. And then we had 2 equations that we had come up with. We came up with our shear equation was 115 kips minus 11.5 kips per foot times x. And then we came up with x was 115 kips minus VU over 11.5 kips per foot, right? And so those were the 2 expressions that we came up with for this problem. The first is given an x value, what is the value on the shear diagram? And the other is vice versa. Given a shear value, what is the location on the x diagram? Okay. So, and then we've got our VU star. VU star, here let me point that value out. This was 91.04 kips. This is 37.95. And this is 18.97. This x value was 80.4 inches. This was 100.2. So is everybody okay with that, with determining that? Okay. All right. So let's begin our design. Let's actually get into this because the design process is not that difficult once you have the shear diagram figured out, but laying it out takes a little bit of thought. Okay. The big thing that we ended with this example, though, is one thing that I need to state. We are going to be placing stirrups from x equals 0 inches to x equals 100 point, not 1100, 100.2 inches. Right? That was the final observation that we made. Remember, from x equals 0 to x equals 80.4 is where we have to have them for strength for strength requirements. Between 80.4 and 100.2 is where the concrete takes over, but we just have to place S max. And anything past that is where we don't need stirrups at all. Okay? Sound good? Now, to start my design, what I'm going to do is I'm going to use VU star. Okay? So what I'm going to do is I'm going to say, based on VU star and based on what we're getting out of our concrete, we're going to determine what our required stirrup spacing would be at the very beginning. Okay, so step 2 is to determine our starting S value. Okay. So our starting S value is computed by saying phi times AV FYTD over VU star minus phi VC. Okay? And everybody's going to write that down, and I want to explain why we're using this expression the way that we're using it. So y'all go ahead and write that down, and I will explain what's going on. Everybody good? Okay. So what I'm doing here is I'm basically looking at this. So I have phi Vn has to be greater than or equal to Vu, and so we compute phi Vn by adding up phi Vc and phi Vs. And so I know what phi Vc is. That's what 38.97 kips or what have you. And so I need to figure out what phi Vs is. Well, phi Vs is phi times this quantity. It's AV Fy d over S. And so really what I'm after is I'm solving for S. What stirrup spacing do I need to provide in order to ensure that my beam has adequate capacity? Now, what I'm going to do for the purposes of this design is I'm going to start my shear design using the shear at x equals d. So I'm starting this design at VU star. So that's why we have VU star there. And so that equation is exactly what it was before, just plugging in VU star. So let's plug and chug this out. So this is big fraction up top, 0.75. 0.22 inches squared. Whoop. 60 KSI. What was D for this problem? 25 inches. And then VU star, I'm not using the shear at the support. I'm using the shear D away from the support. So I'm using 91.04 kips, and I'm subtracting phi VC, and phi VC was 38.97 kips. Now, so did I do something wrong? 37.95. Why did I think 38.97? I don't know where I got that. 37.95 kips. Okay, so what does this come out to be? Okay. 4.66 inches. Do I have a second on that? So what this is saying is that if I want to provide adequate shear capacity in this region right here, and we're assuming constant shear, I need to utilize a stirrup spacing of 4.66 inches, right? Now, I'm not going to go to a contractor or somebody tying rebar and say, space those stirrups out at 4.66 inches. That's a little bit of a ridiculous value. So what am I going to tell them? Space it at what? Now, okay, well, hold on. Somebody said, who said 5? Okay, 4.5. Okay, so the first thing to recognize is that this is the stirrup spacing value that we compute. What you specify is not something larger than this value. It would be something smaller, okay? A smaller stirrup spacing indicates larger capacity. So it's not like with beam dimension. You know how you calculated B is 15.6 inches, so you round it up to 16? Well, with this, you calculate an S is 4.66 inches, you round down, okay? Now, 4.5 inches would be reasonable, and I'm not saying it's not, okay? But what I'm about to show you, I think requires a little bit of mental math, so it's easy to understand. So I'm going to round it down to 4 inches because 4 it's easy to multiply, okay? So we're going to use S equals 4 inches for the sake of this discussion, okay? So let's use S equals 4 inches. Okay. Now, let me explain how this layout will work. Now, what I'm going to do is I'm going to generate a design, okay? We could stop right now and produce a design. And I'm going to show you how to do that right now. We're going to produce a design, and then we're going to improve upon it, okay? So let's look at design number 1. Okay. Now, let me explain how stirrup spacing works. So we're going to use a stirrup spacing of S equals 4 inches throughout the beam. However, when you place your first stirrup, typically what you try and do is usually a very common value for your first stirrup is to either use half that value or to use something like 2 inches. And I'll show you why here in a second. So I'm going to write out verbally what we're going to do. We're going to place the first stirrup at X equals 2 inches. Okay? Then what we're going to do is we're going to use 4-inch spacing until where? Now I'm keeping this design very, very simple, really easy. So I'm going to use 4-inch spacing until X equals 100.2 inches. Why am I stopping it at 100.2 inches? Because past 100.2 inches, the concrete can take over and I don't need stirrups at all. Does that make sense? We're going to start crawling, then we're going to walk, then we're going to run. You're right. You are absolutely right. We're going to get there. Okay?
And the first stirrup is always going to be half of.
Either half or 2 inches, some smaller increment. 2 inches is very common. For your homework assignment, I told everybody to keep it at 2 inches. And I'm going to show you why 2 or 1/2 inches is very common. You'll see that here in a second. So imagine, here's the beam, right? And let's say that the support is right here, okay? So here, that's X equals 0, right? So typically the idea is we'll place that first stirrup 2 inches away and then 4, 4, 4, because the idea is that you could theoretically have a stirrup behind there, and so you would know that that stirrup spacing crossed or it sort of straddled the support, which is why we go with usually half or 2 inches or something like that. It's very common. Is everybody okay with that? Okay. All right. So here's what we're going to do. So we're going to place our first stirrup at X equals 2 inches, so 2 inches away. Then we're going to have a stirrup 4 inches away, 4 inches away, 4 inches away, etc. Okay. All right. Okay. So let me lay that out. So I'm going to have one stirrup spaced at 2 inches, and so that's going to be 2 inches out. Then I'm going to do my remaining stirrup spacing at 4 inches. How many increments am I going to need to get to this? So think about how that math works. So if I do 1 at 2 inches, that's 2. So this is 2, then this would be 6, this would be 10, this would be 14. Everybody see how this is going? What did somebody say? Okay, let's say it was 24. Okay, if I had 24 times 4, that would be 96, and if I added that up, that gets me only 98. So I'm not quite there, right? I have to get to 100.2, or either get to 100.2 or get past 100.2. Well, that's true. Well, but are you talking about from the support or from the end of the stirrups? Because that would only get me to 100. We could. I'm wanting to keep this constant for what we do later because it's going to get more complicated. So I want to keep the value at 2 constant, and you'll see why. You'll see why. You need 25 for this region because 25 here, 25 times 4, that would get you 100. And so if I used 1 stirrup at 2 inches and then 25 at 4 inches, that would be a total range of 102 inches, and that would get me past that. Does everybody see that? I'm starting simple because it's going to get more complicated real quick, so I want to make sure everybody's clear with this. Is everybody okay? So how many stirrups is this total? 1 at 2 inches, 25 at 4, so would you agree that's 26 stirrups? Everybody okay? Now how many stirrups is that? So do we place 26 stirrups in this entire beam? How many do we place in the entire beam? Why do we place 52? Exactly. This only gets us to half to the center line, right? Remember, we're only doing the design from the support to the center line, so we'd have to repeat this pattern on the other end. So 26 stirrups on this half of the beam, but it's really 52 stirrups overall. Okay? So this is 52 stirrups total. Does that make sense? Okay. Now, that was us crawling. Now let's try walking. Okay? And what do I mean by walking? Okay? I'm using baby terminology. You probably see why. What do we need to do now? What was a point somebody raised earlier? Well, that's true, but so what about that center section? That center section, we could use S max, right? Okay, so before we do that, I have a little bit more of an elegant way of handling that. The first thing that we probably need to do is we probably need to figure out what S max is, right? Let's figure out what S max is. So let's go off on the side here, and let's determine S max. Okay, let's determine S max. So now the way that we do that is we have 2 different quantities that we're going to compute. Before I do that, off the side over here, what is 0.75 square root of FC prime? Which is 0.75 square root of what? There we go. You'll see why I'm doing this. Just bear with me. Okay. Okay. I just put that off to the side. Just bear with me. All right. So we have S max 1, which is the minimum of D over 2, or 24 inches. And so that's the minimum of, what is D, 25? What was D? 25 over 2, or 24 inches. And what is 25 over 2? 12 and a half. Okay. That's S max 1. So there's 2 S max computations that we perform. One because the code has a limit on maximum spacing, and the other because the code has a limit on minimum reinforcement. We just rearrange it and solve for S. Now S max 2 is computed by taking AV times FYT over BW times what? Well, if you go to the spec, it's BW times the maximum of either 0.75 FC prime or 50 PSI. So which is the maximum? 50. So you see why I computed this off to the side, because we were going to need it anyways. So the formula is the maximum of 0.75 FC prime or 50 PSI. Well, we know that's 50 because we computed that over here. So we have 0.22, 60, BW. What's the width of this beam? I don't remember. Was it 14 inches? 16 inches. And then this is 50 PSI. Do we have a problem here? There we go, making sure everybody's awake on this Friday. Got to turn that into 60,000. How many was like, oh, I forgot about that? You're like, Dr. Mike, it's Friday. Let's just go. We can't handle the jokes. Just wait till senior design. All right, and so what does this come out to be? Come on, it's concrete design. I'm trying to crack you up. Come on. That was a good one. What's that? What'd you get? Have I not used that one yet? Concrete design. I'm trying to crack you up. Okay, so, all right, back to concrete design. So SMAX1 and SMAX2, which one controls? Like, which one's going to govern what we pick? The 12.5 or the 16.5? The 12.5. Like, we couldn't use a 16-inch spacing because it would violate this limit, right? So we obviously picked the minimum. Now, in order to keep our mental math easy, instead of using 12.5 inches, what I'm going to do is go with something simpler and use 12 inches. Okay. Now, okay. Okay. Now, here's the thing with S equals 12 inches. I have actually a better way of going about incorporating 12 inches. See, here's what I want to do. Let me scroll up a bit. Here's the beam, and what I could do is I could keep this simple, and I could say, okay, start at 2 inches, use 4 inches until I get here, 12 inches until I get here, and I'm good, right? But I would probably bet money that we can probably use 12 inches somewhere in here. See, if I have an S equals 12 inches, I can compute a VS, a VN, a PVN. I can compute the capacity, and then I can figure out where that capacity occurs on the shear diagram, and it'll actually tell me when I can start using S equals 12 inches. So that's what I'm going to do. So step 4 is determine when we can start using that. So determine the range for S equals 12 inches. Okay, so here's how that works. So VS is AV FYT D over S, so that's 0.22, 60, 25 over 12. What does that come out to be? $27.5 kips. Second on that? Okay. Next, what I'm going to do is I'm going to compute phi VN. So phi VN is going to be phi VC plus phi VS. Okay? So that is, what's phi VC? 37.95 kips, plus you do not add 27.5. That's wrong. You add 27.5 times 0.75. So don't forget the phi here. You know, just make sure that you're adding up apples to apples. So you have a phi VC and a phi VS incorporated. So what does this come out to be? 58.58. Okay, all right. Second on that? Okay, now let me scroll back up to the shear diagram because I really want this to make sense. What'd you say? 58.58. So that's about right there. Would you agree with that? So would you agree that I can probably start using S equals 12 inches about there? I mean, think how this works. If I use S equals 12 inches, I get a capacity of 58.8 inches. So instead of starting to use S equals 12 right here, I'm going to start to use it right here. So I'll use 4-inch spacing up until here, 12-inch spacing up until here, and then I'm good. Now, how do I determine exactly where that is? I use that equation. And instead, and for this VU, what do? I plug in the 58.58 kips. So let's see what that is. So X at phi VN is 115 kips minus phi VN over 11.5 kips per foot. So that's 115 kips minus 58.58 over 11.5 kips per foot. And so what does that come out to be? .91 what? Feet. So in inches, that's what? .87 inches. So was that about 59 inches? What did I draw on the graph? What did I draw? A little over 60. Well, I'm not really good at drawing a straight line, but it's about that spot, right? So that I drew that down to like 60 when actually it's probably a little over there. I can't draw, so. But I can make stupid puns. Okay. Okay. So here's what this means. Let's try this again. So now this is going to be design number 2. All right. Now let's write it out verbally so that we understand what we're doing, and let's see if we can do some mental math to try and figure this out. Okay? So what we're going to do is we're going to place our first stirrup at X equals 2 inches, right? Now we have, right now, we have 4 inches, and what else? We have 4 inches and 12 inches, right? So here's what I propose. We're going to use 4-inch spacing until where? When are we going to stop using 4-inch spacing? There you go. The X equals 58.87 inches. And then once we hit that point, then we're going to use 12-inch spacing, hold on, until X equals 100.2. Does that make sense? Yes.
Okay, so see what more so why do we, in the second part, why do we solve for where 4-inch spacing? I'm trying to word this correctly. Okay, so why do we go and worry about the fact that the 4-inch spacing has to go all the way up to 100.2 when we could have solved for the X equals 58 prior to that, and then that way we wouldn't.
Because I wanted you to understand that mental math first. So design number 1 was not ever going to be our final answer. That was me trying to make sure that you understood the pattern. Because what we're about to do now, it's just going to get more complicated. So I was just getting you to that point where you understood what we were doing. So in a real problem, I never would have just laid it out. I'd have just moved, like where we did design number 1, I never would have done that for real. I'd have just skipped it and started my design here. Does that make sense? I'm just doing that so that we all understand the math. Is everybody good? Does that make sense?
You're gonna round up.
Well, you'll give me a second. Now, man, y'all are excited about shear. Okay, so we're going to start off our design. Our design is going to have 1 stirrup spacing at 2 inches, right? Now, we're not going to round up. What we're going to do is this. We're going to say how many increments would it take to reach here? Oh, yes, that would be 2. I'm sorry. This would be 2. So how many stirrup increments will we need to get either to here or past here? 15. What if you used 14? 14 times 4 is 56, right? So that would only get us to 58. But the limit is 58.87, so we need 1 more. Does that make sense? So, okay, so we would use 15 at 4 inches, and so that would be 60 inches. Okay? So at this so when we use 2-inch spacing, that gets us to x equals 2. At 4-inch spacing, where's our x value right here? Are we at x equals 60 or are we at x equals 62, right? So we're at, so this is where the mental math comes into play. So we're at x equals 62. How many 12-inch increments do we need to get to 102? So we're at x equals 62. 4. Does that make sense? Because this is 48 inches. So this is, so we can say this is x equals 2. This is x equals 62. And so that is x equals 110. Does that make sense? Okay. So when we add that up, how many stirrups is that? 1 plus 15 plus 4, that's 20 stirrups. And that goes all the way to 110 inches. Now that's a lot better than what we had before. How many stirrups for the beam? Well, no, for the beam. 40. So by just using another increment, we were able to drop our total stirrup count from 52 to 40, right? And think, if this beam is going to be used 800 times in a building, that's actually pretty significant, right? I mean, think, every one of those stirrups has to be bent and tied into the cage. So if you can reduce that number of stirrups, reduce your stirrups. That's pretty significant, okay? Does that make sense? Now here's the thing. Let's think about this, okay? There's something to be said about how you can only improve the design so much. For example, okay, I have a stirrup spacing of x equals 4 inches and a stirrup spacing of x equals 12 inches. Would you agree that pretty much whatever stirrup spacing I decide to use for this beam, it's probably going to be between those two values. It's going to be between s equals 4 and s equals 12. Everybody be okay with that? Okay. So if I'm trying to improve this design, I can probably only use values in between, something like maybe 6 inches, 8 inches, 10 inches, 12 inches, somewhere in between. Fair point? Okay, so let me be absolutely clear. This is a totally feasible design. Totally feasible design. Oh, goodness. Let me show you one more feasible design. I'm going to show you how I'm going to go about that. 6. Additional increments. Okay. So I'm going to show you something. Okay. So we have 4 and 12. So I'm going to say that we can probably do stuff in between, maybe 6, maybe 8, maybe 10, something like that. Now I could use a stirrup spacing of like 7 inches or 9 inches or something like that. But honestly, I don't really think that the multiplication is going to work very well. I'm trying to do this, in my head, and I'm trying to explain this just so that everybody kind of understands what's going on from a conceptual standpoint. Now let me look at this lower row on the table so that you all understand. What did we do with this S equals 12 inches earlier? We said if you have S equals 12, you can compute VS, and that ended up being 27.5, right? Then we said, well, if you have VS, you can compute VVN, and that ended up being, what, 58.58? Right? And what was X for that? It was 58.9 inches, right? So what you could do is you could just start using additional stirrup spacing increments, and let's just see what comes out. Now, you all are engineers, and engineers should be experts at using Microsoft Excel. So let's just break out some Excel and see what happens. So let's do the lower row. So how did this work? Like, how did we compute VS? Like, how did we do that from 12? What did we do? ASFY times D over S. So that was 0.22 times 60 times 25 divided by whatever that was, right? So I could very easily just copy and paste. And think, as the stirrup spacing goes down, the capacity should go up, right? Make sense? So how did we compute VVN? We said, well, it was 38.97. Was it 38.97? Why am I doing, what am I fascination with this number? 37.95 plus 0.75 times that, right? That's what we got, right? Okay. And then how do I compute X? What did I do? I took 115 minus that value divided by 11.5, right? But then I had to multiply the whole thing by 12. So equals and that's what we got. So everybody okay with that? You could very easily do this either in Excel or by hand. Not exactly the end of the world, right? So let's see if we could improve our design. Let's see here. I'm going to zoom out a bit. Let's see if we could improve this a bit. We place our first stirrup at X equals 2 inches, right? Then let's say for the sake of discussion, let's say I'm just going to use this one. I'm just going to use that one. I'm not going to try and use all of them. We'll say we're going to use S equals 4 inches until we reach X is 37.36. Then we're going to use S equals 6 inches until we reach X is, what, I don't know, 58.89 or 88. Then we're going to use S equals 12 inches until X is until we reach 100.2. So what I'm doing is I'm just adding another increment in between. Like I'm not trying to use 7 increments. All we for our last design we had 2, 4, and 12. What if we did 2, 4, 6, and 12? So we'd place our first stirrup at 2 inches. We'd use 4-inch spacing until we hit here. Then that would allow us to use 6-inch spacing until we went there, and then we use 12-inch spacing throughout. Does everybody see kind of how I did that? Okay, so how would that work mathematically? Like we would have 1 stirrup at 2 inches. That'd be 1 times 2, right? And so if we use 4-inch spacing, how many increments of 4-inch spacing would we have to use till we get past this? What's that? Well, not 19. What's 19 times 4? You're close. You're onto something. So it'd be 9, right? Because 9 times 4 is 36, and so adding these up, that would get you x equals 38, right? See, if you used 8, you'd be backing off 1, right? Okay. Now, what about 6-inch spacing? How many 6-inch increments would we use to get to 58? Would we use 3? See, how many would that get us to? This plus that. Not quite there, right? Got to use 1 more. Right? Now, how many do we use to get to 100.2? Do we use 1? That's not enough. What about 2? That's not enough. Is 3 enough? No. Got to use 4. Does that make sense? So how many stirrups is that? How many stirrups is that? $18 stirrups? So how many stirrups overall? 36? So by throwing in another increment, see how we were able to shave off a stirrup or 2? Now, here's the thing. You could get nuts with this. You know, you could say, well, I'm going to use 4-inch spacing, 6-inch spacing, 8, 10, 12. You could get crazy with it, okay? And I'll say this, there's a cap on your economy. Like there's a point where you could throw in 3 more increments and you might not actually reduce the total number of stirrups overall. So the question is, are you really going to make it that much more complicated for the contractor and the folks tying rebar? You know, just keep it simple. So I'll be honest, on most beam design problems, you'll never see me practically use any more than 3 increments. And so that's what I'm really using here. I have an increment of 4 inches, 6 inches, and 12 inches. And that I think is pretty efficient. Now, if we're talking about a bridge girder, it's a different story because the shears are so much larger and you only have like 4 or 5 beams maybe on a given bridge, so you actually have the space to tailor that a bit. Yes?
In the actual application of this, we're building from one side of the halfway point.
Yes, so you would mirror it on the other end.
When you mirror it, what happens with the overlap where it passes to 100.2?
That's a great question. It's not going to pass that because where is midspan? Midspan is 120. Yeah, so that's no, we're only laying, that's a fair point. If you were laying this out and you hit past 120, stop, you know, because you know you're going to hit the other end. So that's a fair point. Usually that doesn't happen unless you have some different loading scenarios. So it is very possible in your situation that would happen if you had, instead of a distributed load, if you just had a point load right in the middle. Because what would happen is you'd have this really high shear throughout the entire beam. So it'd be very easy to design a pattern that overlaps. And so if you have a point load, this changes. And the next example, we've got point loads. So it changes the shear diagram. The procedure is the same. The procedure is the same. But some of the details change because we've got concentrated loads instead of distributed loads. So, what do we think? Any questions? You're right. That's exactly right. The code says you don't have to have stirrups, but what you want is if I'm using 12-inch spacing, I want that region of 12-inch spacing to cross that line where I don't need it. I don't want to stop short. What do we think? So if you're wondering what is the answer, okay, what I would say is this is your answer, the design, okay? So there are, for this problem, we came up with really two answers that I would say would be acceptable. One of those answers is this. That's an answer because that is the design. We put one stirrup here, we put 15 stirrups at this spacing, we put 4 stirrups at this spacing. That is an answer right there. Another answer is 1 at 2 inches, 9 at 4 inches, 4 at 6 inches, and 4 at 12 inches. That is an answer as well. Because I'm sure you're like, okay, I get what you're talking about, but what's the actual answer? This is the answer. So you can see that, I've got two different designs. This design is a little more intricate, but ultimately uses less steel. Again, I think it's a trade-off. For this problem, I think using 3 increments is fine. If I was designing building beams, I probably wouldn't use more than that practically. Bridge girders, that's a different story. You could very easily throw in a few other increments if you can shave some shear reinforcement. What do you think? So what we're going to do on Monday, just so you're aware, so what we did just now was this example with a distributed load. What we're going to do on Monday is what if we have point loads, okay? Because what do point loads do to your shear diagram? Pop quiz. From CE 312. It changes the shear diagram. Man, give you a blue ribbon. Holy. Say it again? Yeah, because remember you go up and then boo, right? Remember you're drawing the shear diagram, says, Greg, go down. Okay, I'll go down. Right. Remember that? Well, that sudden drop in your shear diagram will change how you lay out the stirrups. But really another thing that can happen is, those equations that we were using to solve for x? Remember that? Well, you can actually get some wonky answers, and if you don't refer back to the shear diagram, you can get like x's that are negative. You go, what? It's because you're not looking at the shear diagram as a whole. So we'll tackle this on Monday. I'll give you a little bit of a heads up. This is our last example on shear, okay? We're going to tackle this on Monday. To be honest, we probably won't finish it, but I'll do my best. I'm not going to rush through this because this is kind of important. We're going to go through this on Monday. We'll probably have a little bit on Wednesday, and whenever we finish this example, we're done until we come back from spring break. Okay? So, yeah. That's all I got. We'll see you in 10 minutes. What's up?
What if there's a triangular load?
I'll answer that question real quick because that's a very fair point. What if there's a triangular load? Or better yet, what if there are loads that are non-symmetric? If there are loads that are non-symmetric, you can't do what we've been doing where we've just been designing halfway over and then mirroring. You're going to have to determine a layout across the entire beam. That's the short. And if you have a triangular load or something weird like that, then you're just going to have an odd stirrup spacing pattern across the board. And so in those instances, it might just, you're just going to have to play around with spacings to get something that worked, but I would keep it simple for your sake as the analyst and for the contractor's sake. So. Sound good? That's all I got. I'll see you all in 8 minutes.